Welcome back to HackCode. In this video, we're tackling an essential problem for coding interviews, house robber from LeetCode. This problem is great for learning dynamic programming and recursion techniques. We'll explore four approaches: brute force and dynamic programming, top-down, bottom-up, and a space-optimized version. So let's break down the problem step by step and understand how the solutions work. So sit back, relax, and let's dive in. So firstly, let's look into the problem statement. So what is the problem statement? So you are a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is the adjacent houses of a security systems connected, and it will automatically contact the police if two adjacent houses were broken into on the same night. Given an integer array nums representing amount of money of each house, return the maximum amount of money you can rob tonight without alerting the police. So problem is very simple, right? So basically we have some set of houses, and these houses have certain security system. This security system is arranged in such a way that if two houses were broken into on the same night, that would contact police automatically. So basically this robber has to rob like this house and this house. He can't rob this adjacent houses, and we have to return the maximum amount he can rob. Okay, so that's the idea, guys. So if we consider this house, then he can rob this and he can rob this. So let's look into our example one. So here we have nums is 1, 2, 3, 1. So basically we have this four houses, and each house has money 1, 2, 3, 1. So in this case, if we rob this house, he can't rob this house, but he can rob this house. So that case, what we have, the total amount is 1 plus 3, which is 4. Okay. And second way, he can rob this one, and he can skip this one, and he can rob this one. So basically 3. So here the maximum amount he can make is what? 4. That's why we return 4, saying that it's the maximum amount we can rob without contact the police. Okay. In example 2, the nums is given as 27931. Here the output is 12. Why? Because here the robber chooses to rob the house 1, which is 2. Next he chooses to house 3, which has value 9. Next house 5, which has a value 1. So that case 2 plus 9 plus 1 is 12. So he would get the maximum amount. So if it is another case, like if he choose to rob this one 7 and 3, that would be 10 only, right? 12 is greater than 10. That's why we return 12. Okay. So what are the constraints given? Num's length is the inclusive range of 1 to 100. So what we need to look from this constraint? So basically we know that we can perform 10 power 8 operations per second. So here if we consider the case of 10 power 2, which is the upper limit of num's length we have, if we apply whole power 4, it is what? 10 power 8. So that means that we can perform n power 4 operation per second. So that means that the solution is accepted till of n power 4. But we can solve this in optimal way. So here we can approach this in n square complexity. So this is the maximum time complexity which can be accepted for this solution. So that's what I'm saying here. So this is the maximum possibility. It's not that it's the minimum thing. It's the maximum we can go. So anything less than or equal to n power 4 complexity is accepted here. Okay. So in the second constraint, they're given us nums of I is in the inclusive range of 0 to 400. So basically each element in the nums is in the inclusive range of 0 to 400. Okay. So this is the boilerplate code given, wherein we have a method rob which takes nums. This nums is nothing but list of integer, and it returns the integer. This integer is what? This is the maximum amount he can rob without alerting the police. Okay. So let's look into the approaches. Before we get started, I want to remind you about our exclusive blind spot info post. This carefully curated collection covers essential coding interview problems to help you master the most common patterns and excel in your interviews. Whether you're prepping for FANG level interviews or just sharpening your problem solving skills, these problems will ensure you're ready for anything. Even if the exact questions aren't asked, they cover all the important patterns. So be sure to check out our playlist and stay ahead of the competition. So let's look into approach 1, which is brute force with recursion. So what is the intuition here? The key intuition is to decide whether to rob each house or skip it. As we can't rob two consecutive houses, we can use recursion to evaluate every possible path, choosing either to rob the current house and to skip the next one, or to skip the current house and proceed. So basically here we can't rob the two consecutive houses, right? So for that we can either choose the current house and we can skip the next house. The other cases we can skip this current house and we can rob the other house, which is second one. Okay. So that's what the idea is. Just is a basic thing we just discussed already. And here let's look into the algorithm. So here, what is the algorithm? Basically, we have to define the recursive function. And that's why we start with defining the recursive function in the step 1. So define a recursive function that takes the index of the current house and it returns the maximum profit we can earn from that index onward. Okay. So in the step 2, if the current index is beyond the last house, return 0, as there are no more houses left to rob. So this makes sense, right? So basically, if the index reaches the length of the house, that means that it's not a valid case and all the houses are processed. So it is that check. So basically, we know that the valid index is in the range of 0 to length of nums minus 1, right? So if it reaches nums, then it means that all the houses are processed. So that's why we return 0. As there are no more house to rob and he won't get any value out of that. So that's why we return 0. It is that representation. In step 3, for each house, calculate the maximum of 2 choices. That is, rob the house, and like for robbing the house, what we have to do, we add its value and skip the next house. And other choice we have is skip the current house and consider the next one. So these are 2 choices we have for each house. So we have to evaluate the maximum of these 2 choices and store it. So basically we require the maximum amount he can steal, right? So that's why we choose the maximum out of these 2 possibilities at each step. In step 4, we return the maximum of 2 choices. That's all. Okay. So let's look into the code. It's just what we discussed in an algorithm, but in the form of code. So firstly, we define this recursive function, which takes the index, which is of int, okay, and it returns the int. So this integer is what we know, right? It is a maximum profit we can earn from that particular index onward. So first case, the base case. So this is required because if there is no base case in the recursive function, it keeps on calling itself and it would give us recursion depth exceeded error. So that's why we require a base case to stop somewhere, else it would keep on calling itself, okay. So this is the base case where like index is greater than or equal to length of nums. That means that there is no valid index. Oh, we have to return 0 because he can't get any value from robbing and there is no more houses left. That's why we have to return 0. So this is that representation we discussed. And in step 3, we return the maximum of robbing current house and the next house. So if we rob the current house, what is the value we're gonna get? So we just choose nums of index. So currently what index we have, that value we get from the array, which is nums here. This stores the amount, right? So here they given, right? So basically this stores the amount and then plus helper of index plus 2. So if we rob the current house, we can't rob the next house. That's why we pass the index plus 2 to the recursive function, okay? And then we store this in the rob current. So what if we skip the current and check next? So that possibility is stored in skip current. So skip current is equals to helper of index plus 1. That means that we skipping the current house and then we checking the next house. That means that we actually robbing the next house. So that is index plus 1. Because here we are not robbing the current house, we pass the index plus 1. This explores the possibility of robbing next house, okay. In step 4, we had to return the max out of these 2 possibilities, which is max of rob current and skip current. So this is the function we have which returns the max out of these 2 values passed, okay. So at the end what we are doing, we're just calling this recursive function from the 0th index. Basically from the 0th index only we have to process it. That's why we're just calling this from the 0th index we have. So what are the complexities here? The time complexity is O of 2 power n because each house generates 2 recursive calls. So if we consider the case where here we have 4 houses. So for each house we have to decide either to rob or not rob. So each house has 2 possibilities. So 2 into how many times we have to perform this calculation till n length. So that's why it's 2 power n, okay. N length is what? Length of nums. So it is O of 2 power n. And the space complexity is O of n due to the recursion stack we have, okay. So I got the code ready here. Let me try running this. So this is the active solution for the 2 cases. Let me try submitting this. So guys, we see that time limit is exceeded because this is the exponential time complexity and this can't be scaled for the larger array. Okay, so here only 48 out of 70 test cases are passed. Okay, so that's why we need to optimize the solution further. Okay, now let's explore the optimized solutions, okay. So now let's look at the recursion stack we have. So basically for the example 1, we have nums is given as 1, 2, 3, 1, right? So here we output 4. So this is the recursion function we have. So helper of index and for each thing we know, right, we just have 2 possibilities, rob current and skip next. So we call index plus 2 or else like we can skip the current and rob next, which is index plus 1. So now let's look into the calls we have. So firstly we start with sending our index of 0. Okay, so from this we have the 2 choices. We rob the current and skip next. So for that we have to send index plus 2 as we discussed. So index is 0 here, plus 2 is what? 2 only. So totally here index of 2. So we call for index of 2 and then next thing is what? We skip this current and rob next. That means we have to pass plus 1, which is 1. So this generates 2 calls. Okay, from here also we have 2 calls, plus 2 and plus 1, plus 2 and plus 1 here also. So this many calls we have. But let's take a closer look now. So what we have actually, we are actually redundantly calling this again and again. So if you see this index of 2, only for the small problem, it is called for twice. So index of 3 is called for 3 times. First is here, next is here, and next is here. So similarly, index of 4 is called for 4 times. Here is 1, here is 1, here is 1, here is 1. So basically, same way we have index of 5 is called for twice. So what you are observing here, so basically this has been called again and again, which is redundant, right? So what if we store this result in our cache or some memory so that we don't need to compute it again? So basically we can use this subproblem again for computing the larger problem. That means that we are avoiding this redundant computations. So that will save us some time. So that would give us a better time complexity. Essentially, I'm talking about this dynamic programming, okay, which is nothing but we solve our subproblems and store results, and then we use this subproblem result to solve the bigger problem, okay. So now let's look into the top-down dynamic programming approach, which is nothing but a memoization approach. So this is basically same as previous approach, but we just use a memoization concept, okay. This recursive approach repeats calculation for the same indices. Using the hash map for memoization, we can store results of previously computed states to avoid redundant calculations and speed up the solution. So basically, we use certain memory, right? That memory is the hash map data structure here, or dictionary in Python, okay? So the algorithm is pretty much same. So firstly, we define a memoized recursive function that takes index of the current house and stores the maximum profit for each index in the hash map. So here hash map is our cache, okay? So in step 2, if we already have the result for the current index, return it from the cache. In step 3, similar to the previous recursive approach, we calculate the max of robbing or skipping the current house. In step 4, we store the result in the hash map and return it. So basically, the idea is what we are doing. Firstly, we check in the cache if the value is computed. If it is computed, well and good, we just return it. If it is not computed, we compute the values in the recursive calls and then we store it in the cache, and then at the end we return it. So there is one layer of checking required here. Basically, before compute we check, after compute we store and return. That's the idea, guys. So this is pretty much simple as a previous approach. Just we have a hash map. So later point of time in the video, I'll show you how to just add a one line and make it as a memoized version. So basically for recursive function, if we just add one line, it would become a memoized version. Okay, now we just added some few changes. Let's explore the changes we have added so that it will give you an idea. Okay, so here firstly we insert the hash map. This hash map is what? So basically to store the computed results, right? So this hash map is dictionary in Python. So here we have the same recursive function which is defined as in previous approach. Okay, firstly here we check in the base cases, okay, and then next what we do, we just check in the cache. So if index is in memo, we just return the memo of index, okay, we return the cache result. So this is the additional step here we have. Next is the same step we have, so rob current and skip current, okay. So this is where we have some changes. So here we are actually returning, right? So before returning, here we are storing that in the memo of index, and then we return the memo of index, okay. So this is same, guys, just that we have some memo added here, okay. We just store in the cache before we return, that's all. So what are complexity here? The time complexity is O of n, because each house is only computed once, okay. So if you have n houses, we compute it only n times, okay, because store it in our cache, we don't recompute this subproblem again. That's why it's only O of n, okay. And the space complexity is O of n for the memoization cache and the recursion stack. So basically this takes n space and the recursion stack also takes n space. So it is totally 2n, but 2 is ignorable constant, so it is n, okay. So now guys, I told you, right, with just a single line change, we can make it memoized version. So let me just do add cache. Basically this is a decorator which stores the value of this recursive function, okay, for this particular index. Okay, so next time if it gets called for the same parameter, then it would look into the cache before computing. So it's the same idea of hash map, but we just use a decorator here. So now let me just submit in this. So see, this accepts solution and beats 100% of users. So this is the same as previous approach. We just added a simple add rate of cache, okay. One thing to keep in mind is this cache support is added from Python 3.9 plus. If your compiler only supports Python 3.2 plus, you can use LRU cache, okay. So it's just a add rate of LRU cache. So let me try summon this. Now this also beats us 100% of users, okay. So basically the difference between the cache and LRU cache is there is a memory constraints here. So if you specify the max size as some 4, so let me specify the max size as 4, then it would hold only till 4 elements. So rest all it would have it based on the least is unused. So basically if you don't specify this max size, it would be none by default. In that case, it would behave same to cache, okay. And in cases where your interviewer don't accept this approach of using the add rate of cache or LRU cache, you can propose this approach, okay. So this approach is nothing but using the hash map here. So now I got the code for the memoization with hash map. Let me try running this. So this accepts solution for the 2 cases. Let me try summoning this. So this also beats 100% of users. Cool, right? So now let's look at the bottom-up dynamic programming approach. This is basically a tabulation approach instead of the memoization. So here we will be doing iteration in place of recursion, okay. So what is the intuition here? In this approach, we leverage the dynamic programming array to keep track of maximum amount of money that can be robbed out to each house. So here in array, each element keep holds of maximum amount of money that can be robbed till that house. Okay, the key idea is to decide whether to rob each house or skip it based on the maximum amounts calculated for previous houses. By filling the DP table iteratively, we ensure that we always consider the best possible outcomes at each step. The iteration is almost same, but here we use a iteration instead of recursion. So that's the only difference here, but it almost looks same. Okay. So what is the algorithm here? If there is only one house, return its value. So basically here num's length is an increase range of 1 to 100, right? So for the case where we have only one house, this is the base case, then we have to return its value. Basically, if there is no other house left, he can rob only that house, right? So that case, we have to represent using this step. Okay. So in step 2, create a DP array of same length as of number of houses, which is initialized to 0. So basically here each element in the DP array should keep track of the maximum amount of money that can be robbed till particular house, right? So if we have n houses, we have to create a DP array of length n. So that's what the idea is. So step 3, set the first element of DP array to the value of the first house. So DP of 0 is equal to nums of 0. So makes sense, right? So basically this should represent the maximum amount of money that can be robbed from first house. So nothing but nums of 0 only. That is the first house value only, representing the maximum amount that can be robbed only if the first house is constant. In step 4, set the second element of DP array to the maximum of first and the second house. That is DP of 1 is equal to max of nums of 0, nums of 1, representing the maximum amount when considering the first two houses. So when we consider first two houses, we have only one choice. We have to rob either of them. So in that case, we choose the maximum value, right? So this is that case. Okay. In step 5, iterate to the houses starting from the third house, which is index 2. For each house, we store the maximum amount that can be robbed up to that house. Okay. So this is what our DP array should contain, right? So that's why we're just picking it for the each step. Okay. If we rob the current house, the value is DP of I minus 2 plus nums of I. So basically here the value of DP of I is DP of I minus 2 plus nums of I, because we robbed the current house and previous to previous house. So basically here we skip one house in between and then we rob the current house. Okay. So that's why DP of I minus 2 plus nums of I. So DP of I minus 2 stores what? Maximum amount that can be robbed till I minus 2 houses. Okay. So that's why we just do the addition here. Other case we have is if we skip the current house, the value is DP of I minus 1. So if we don't drop the current house, then what it is? So basically it is the same value we can drop till I minus 1 houses, right? So that's why we just keep the same as this one. Okay. So this is the maximum amount from the previous house. In step 6, return the last element of the DP array which contains the maximum amount that can be robbed. Okay. So basically last element is what? DP of minus 1 or the last index. So last element shows what? Till that houses, what is the maximum possible amount? So that's why we have to return the last element. Okay. So let's look into code. So firstly, we're handling the base case wherein nums of length 1. In that case, we just return the nums of 0, which is the first element we have. So next, we just get the length of the nums stored in n. So this would be used for our further iterations and computations. So firstly, we are inside the DP array of length n filled with all zeros here. Here, if you don't get this, let me just explain you. So firstly, we have a list with element 0. Let me just execute it. So we just get the 0. So what if we multiply with 4? We get 4 zeros. Let me just show you. So that means that if we multiply with n, we'll get a list of length n, all elements filled with 0. Okay. So that's what the idea there. So next, in step 3, we are considering the maximum if only we have the first house. So if there is only one house, that means that we just get the value, right? So we just get nums of 0. There is no comparison required for that. So DP of 0 holds nums of 0. So and for DP of 1, what it is the maximum amount we can get if we drop 2 houses. So if we have only 2 houses, we just pick the maximum out of this house, right? We don't have other choice. We either we have to choose this house or this house. So in that case, we just pick the maximum of these two values. So that is for filling DP of 0 and DP of 1. And the rest of the cases are generic. So we just iterate from the third house and fill the rest of the cases. So firstly, what we know is we just need to take the max out of 2 possibilities we have. So what are the 2 possibilities we have? We rob this house and skip the next house. Else we skip this current house and then rob the next house. So this is the possibility of skipping the current house. So if we skip the current house, what is the maximum for the DP of I? It is just what we have out previous. That's why we pick that maximum DP of I minus 1. And then if we choose to rob the current house, then we just add this to the previous maximum we have. So previous maximum is what? DP of I minus 2 plus nums of I, which is the current house value. Okay. So DP of I would store the max of these two values. Okay. So at the end, we just return the maximum amount that can be robbed from all the houses, which is DP of n minus 1. Or else we can access using the DP of minus 1, which is the last element, right? So basically, DP of I stores what? Maximum amount that can be robbed till I houses. So if we pick DP of n minus 1, so it would give us the maximum amount we can drop for all the houses. That's why we're just picking the dp of -1, which is nothing but dp of n minus 1. Okay, so this just acts in the last index. Okay, so what are complexities here? The time complexity is O of n as we compute the maximum profit iteratively for each house. So here we have only one for loop, and then we are iterating for n minus 2 times. Okay, and then here it is 1, so that's why it's just like O of n minus 2 here in this for loop, but this 2 is negligible, so that's why it is O of n. The space complexity is O of n for the TP array to store the intermediate results. Here we use a TP array of length n, right? So that's why it is O of n space complexity. Okay, so I got the code ready here. Let me try running this. So this is the ASCII solution for these two cases. Let me try submitting this. So this is ASCII solution for all cases, and it also beats the 100%. Okay. So now let's look at the space optimized dynamic programming approach. So here the time complexity remains same, but the space complexity would be optimized to O of 1. So why is this required? So basically, if you see in this previous approach, we are using only 2 elements for computation for the current iteration. So that means that if you store the 2 variables, then that's enough. So this approach is all about maintaining 2 variables instead of the TP array. So let's look at the intuition. This approach leverages the idea that at any given house, the maximum amount that can be robbed only depends on the maximum amount from the previous 2 houses. Okay, this was something we just discussed, right? So instead of maintaining a full TP array, we can keep track of just the last 2 maximum amounts using the 2 variables, thus optimizing the space complexity. So basically here space is much reduced than that, right? We're just using 2 variables, which is constant space. Okay, so algorithm remains almost same, but just we are storing 2 variables instead of a TP array. So if there's only one house, we return its value. Okay, we know this, right? So basically if it is one house, there is no other way, we just return that value. So in step 2, we use 2 variables, max amount previous one and max amount previous 2 to store the maximum amount up to the last 2 houses. So step 3, set the max amount previous 1 to the value of first house and max amount previous 2 to the maximum amount between the first and second houses. Here you got the role of these 2 variables, right? So basically the idea is this max amount previous 1 should store the maximum amount of money that can be robbed from first I minus 1 houses, and this variable should store the maximum amount of money that can be robbed from first I houses, that is from index 0 to I. Okay, so that's why when we considering for the 2 houses, we are considering the max of this 2 houses. Okay, in step 4, we iterate the each house starting from the third house, that is index 2. For each house, update the current maximum amount by deciding to rob the current house, adding its value to the max amount previous 1 or skipping it, keeping the max previous 2. So basically you got the idea, right? It's the same thing. In step 5, update max amount previous 1 and max amount previous 2 for the next iteration. And step 6 is nothing but just returning the maximum amount we have. So at the end, return the max amount that can be robbed. Okay, so the idea is same, just that we use the 2 variables. So even if you look into the code, almost same. Okay, so here first step we just handling the base case, this is similar to previous approach. In step 2, here we insert the 2 variables instead of the DP array we have. Okay, so here we insert the max amount previous ones. So here this is similar to DP of 0. So basically here we're storing the max amount we can rob till first house. Next thing, we're inserting the max amount previous 2, and this would store the maximum amount of the first 2 houses. Okay, in step 4, iterate starting from the third house. This is same to previous approach. So here the range starts from 2 and then it ends at length of nums minus 1. Basically this is exclusive, right? That's why. So here we decide to rob or skip. So if we decide to rob, we add the current nums value to the previously robbed thing, that is max amount of previous 1. So I just told you, right? So this max amount previous 1 holds the maximum amount of money that can be robbed from first I minus 1 houses, and then this max amount previous 2, this holds the max amount that can be robbed from first I houses. Okay, so that's why here if we don't rob this particular house, that means that we can just continue with the previous house. So we just store the max amount of first 2 houses here, so we can utilize the same if we don't rob the current house. Okay, in step 5, we have to prepare this variable to the next iteration. That means here max amount previous 1 would become max previous 2, and then max previous 2 would become current max. Makes sense, right? So this should hold till I houses and this should hold till I minus 1 houses. That means that previous one would go to this value and the current one would go to this value. That's how max amount previous 2 would hold the max amount till I houses. Okay, so in step 6, we return the maximum amount. So that is just the value of this max amount previous 2, because the current max amount would be stored into this one, right? So that's why we just return it, and this would hold the maximum amount we can make from n houses. Okay, what are complexity here? The time complexity is O of n because we iterate to the list of houses once. So similar to the previous approach, in the for loop we iterate till n minus 2 times, and then this 2 is negligible. That's why we have O of n time complexity. And here the space complexity is O of n, since we use only 2 variables to keep track of the maximum amounts. So basically here we were using the TPRA, which is of length n. So that's why it is often. But here we're using only two variables always. So here the storage size doesn't increase with the size of the input. So it's always constant and two variables. So that's why it is one, which is constant space. I got the code ready here. Let me try running this. So this access solution is two cases. Let me try summoning this. So this access solution for all the test cases we have, and also it's 100% of users. Cool, right? And that's a wrap on solving the house strawberry problem using 4 different approaches. If you found this breakdown useful, drop a comment below and share your thoughts. Don't forget to like the video, spread the word to your fellow coders, and hit the subscribe button for more in-depth coding tutorials. Also, do follow on Instagram for the latest updates. And if you're looking for resources or have some doubts and want to discuss, join our Telegram community. See you in the next one.